You already know how to describe motion, quantities like velocity and acceleration. But to understand the cause behind that motion, we look at the science of dynamics. Dynamics is centered on the concept of force. A force is a physical push or a pull applied to an object. It is the interaction that makes a ball start moving, stop, change shape, or turn. Newton's first law, the law of inertia, explains objects maintain their current motion unless acted upon by a net force. When a cart stops suddenly, the water inside a bowl keeps traveling forward because it's inherently resistant to changes in motion. When a net force does act on an object, we use Newton's second law to calculate the result. This equation states that net force equals mass times acceleration. The sigma symbol means we are summing every individual force acting on the object. The m represents the object's mass, or inertia, and a is the resulting acceleration. This relationship also reveals that if the forces pulling on an object perfectly balance out, the net force is zero. In this state, the acceleration is also zero. The object is either perfectly at rest or moving at a constant speed in a straight line. Finally, Newton's third law states, for every action, there is an equal and opposite reaction. These forces act on different bodies, so they don't cancel out. When a fist hits a brick wall, the wall exerts the exact same force back into the hand. Together, these three laws allow us to quantify how any given set of forces will change an object's speed or direction. To apply these laws to a specific problem, we start with a free body diagram. This allows us to isolate an object and map out every force acting on it. Consider an 8-kilogram crate on a frictionless slope angled at 30 degrees. Our goal is to find its acceleration as it slides down. First, we add the weight vector. Gravity pulls the box toward the center of the Earth, so the arrow points straight down. Next, the ramp exerts a normal force. A surface always pushes back perfectly perpendicular to itself, so we draw this arrow pointing away from the ramp surface. Using standard vertical and horizontal axes here makes the math difficult because the box is accelerating diagonally. Both its x and y coordinates are changing simultaneously. To simplify the calculation, we can rotate our coordinate system. By tilting the grid 30 degrees, the x-axis now aligns perfectly with the surface of the ramp. Now our motion is restricted to a single axis. Since the weight vector is no longer on a grid line, we use trigonometry to break it into two components, one pulling into the ramp, w cosine 30, and one pulling down the slope, w sine 30. Focus on the x-axis parallel to the slope. Using Newton's second law, pause the video and try to solve for the crate's acceleration. On the x-axis, the only force is the component of weight pulling down the slope, w sine 30. When we plug in our values, 8 kilograms times gravity times the sine of 30, and divide by the mass, we get an acceleration of 4.9 meters per second squared. On the y-axis, there is no motion. The box isn't lifting off or sinking into the ramp, which means the normal force must exactly balance the component of weight pushing into the surface. Rotating the coordinate system allows us to take a complex two-dimensional movement and solve it using simple one-dimensional equations. Now consider a more realistic scenario. What if the ramp surface is rough? This introduces kinetic friction. Friction always opposes the direction of motion, so as the box slides down, the friction force points back up the ramp. To find the new acceleration, we adjust our net force equation by subtracting the opposing friction from the component of weight pulling the box down. You can solve any dynamics problem by following 5 steps. First, draw the free body diagram. Second, choose or rotate your axes to align with the motion. Third, resolve off-axis forces into components. Fourth, set up the net force equations for each axis. And finally, solve for the unknown variables. Following this sequence allows you to isolate individual forces and solve for the resulting motion of any mechanical system.